Now let us discuss continuity, or the idea of continuity of a real valued function using these four examples. Okay, so let's consider this function x times cosine x, and so let's look at a graph here. And if you look at this graph, the graph of the function, seems to be flowing continuously as you go along the x-axis. Okay, and we may say that this function is continuous at every real number, even though you see the window only from -5 to 5. But soon in our analysis you will see that because of the factors that it's composed of, this function will be continuous along the entire real line. Now next, let's consider this function that we have discussed before. Okay, so this is the function, and we know that it is we cannot define it at we cannot find a value for it at 0 by using the expression. So let's look at a graph again, and you can see this here, that is well, we know that the function is not defined at 0. Still we see 0 covered there in the graph. So since we know what we are doing, we can go ahead and modify the graph. One sec. Okay, so we know that this just can't be true, that we have the graph covering this function at 0, even though we know that it is not defined at 0. So here we have a discontinuity at 0. Okay, and everywhere else you can just go and expand the window and see that the function is continuous. Let's look at another one, say right here. In this one, we will expect a discontinuity at x equals 1 because the function is not defined there. And indeed, there is discontinuity at x equals 1. You can see that there is a big break in the graph. On the right of 1 it is 1, and on the left it is -1, and we can add two little circles here to show that there will be holes at this point, or these points. Okay, then let's look at this function that we discussed, the greatest integer value function, which is defined by this expression. And what we mean is this, that say if you look at 0.7, then this is the greatest integer less than or equal to 0.7, which we know is going to be 0, right? Say for instance you type in 1.7, okay, then the value is going to be 1. And if we write the value at say -1.7, then what's the greatest integer less than or equal to -1.7? That number on the left will be -2, as you can see. And say we look for the value at say pi. All right, where is pi? Right here. Then it's 3.14 approximately, so that you would expect the value is 3. Okay, so if you look at this function here, then this function has many points of discontinuities, right? It is discontinuous at every integer value, and here you see it extending further on this side. Actually, yeah, there is a little, I would say, little different thing. Now it's much better. And of course, to stress that it is discontinuous from the left here, we can put a hole over here. We can use again our paint and brush feature. okay, to just stress the true nature of this function. Okay, so here let me erase it and get down to this one. So we can do this. So at this point it is not continuous. This is discontinuity. Then again we have a discontinuity here, and here I think we will have to add a tiny circle to show that. Okay, and so here we go. Okay, why don't we copy it so that we don't have to make it again and again. Okay, so this is the situation here. Then same is the situation at this place, and we can go on finishing it off. And for the places where it changes its nature, we can do this, like just we can stress that here the value is 0. Just a moment. Okay, and then for this one the value is 1, and you can go ahead and finish modifying the whole graph like that to get the real idea. Now we examine the problems that occur at the points of discontinuity. Like in this case, at x equals 0 the function is discontinuous, and what we have is that the limit is available, but the function is not defined at x equals 0. Okay, now this greatest integer function has many points of discontinuities. Say let's take 1 for example. The function is discontinuous here, and the problem here is that we have the value of the function at 1 is available, but the limit is not available. Okay, and if we look at this function, this is step function, which we define by this, and in which we are lacking definition at x equals 1, but at the same time the limit is not available either. So we are going to call a function f, which is defined on an interval containing a, and just note this, that at this time we need the definition at a as well. To be continuous at a, if we have what? We must have the limit of the function available at that point, in this case meaning the point a. All right, and the limit must match or must equal the definition or the defined value of the function at a. Okay, so go ahead and read my commentary on continuity, and if you have any difficulty, ask me, and I shall either write more explanation or if necessary make a video on that for you. Okay.